Hello, welcome to Quantum Algorithms and Cryptography. So today our goal is to get deeper into the ideas that we started talking about last time, and in particular we'll discuss the basics of quantum information. So before we even define quantum information, I'd like us to take a small step back and just think about how we proceed with this, right? So what is meant by a model in science? In general, as you know, the universe is complex, it's strange, it's fascinating, it's full of diversity. You have living organisms like bacteria and viruses. Everybody knows about viruses in great depth now because of COVID. And you also have, mechanical wonders like airplanes, you have trees, planets, so on and so forth. And what is our method of understanding any of these objects? Right? We'd like to understand all this diversity, try to make sense of all of this by abstracting out the principles of observed phenomena in the simplest possible form. Right? So, we'd like to work out abstract principles, and then these should be able to not only understand the observed data, but should also be able to predict behavior in instances that have not been observed. Right? So, that's what we're also going to try to do here, and the bedrock of our effort here is the fact that information is also physical. So, even though we think of information maybe as some abstract bit strings in our head or numbers or sentences in our head, finally it is something that has a physical existence. So, for instance, if you want to compute on it, you have to store it somewhere, and how you store it, this matters, right? So, for instance, in the classical setting, we're used to storing it like in a binary form. So, something that is either 0 or 1, and this could be captured or this could be represented by different voltages, for instance, or different spins of an electron, or whether you have the quiet or the excited state in an atom, right? The ground or the excited state in an atom. So, there are various different ways in which we can represent 0 and 1, and what all of quantum computing makes use of is this amazing fact of quantum mechanics, which is saying that actually all this information is also going to be subject to quantum laws, right? And what quantum laws tell us, we are going to see more in detail today itself, but what quantum laws tell us is that things are not just 0 or 1, but in fact they can be both somehow at the same time. So, as you see in the picture here, right, the classical idea of a bit that we have, which corresponds to sort of classical mechanics or Newtonian mechanics, can be generalized into this quantum idea, a qubit, right, which says that in fact a quantum bit is something which is what's called a superposition of both 0 and 1. So, it is neither and both at the same time somehow. We are going to make this precise very soon. So, let's start with some basic formalism over here. Let me refresh our concepts first on basic things like complex numbers. What's a complex number? As you know, it's a number of the form a plus bi, where a and b are real numbers and I is the imaginary root of -1. Okay, so in particular, if we want to write down an example, let's write down some number z, which is a plus ib. So obviously here the real part, what is it? Well, obviously it's a, right? And the imaginary part, this is b, okay? And we can also represent a complex number in polar coordinates. You can see here a picture of the argand plane, right? So, here there is a complex number z. The x-axis is the real part, the y-axis is the imaginary part. So, if I want to write z in terms of the polar coordinates, then well, it is mod z cos theta plus mod z sin theta, this is the imaginary part, right? And the length of z here, so the absolute value of z is going to be you know, square root of a square plus b square, right, where a is cos theta and b is sin theta. All right. Good. And obviously, I should also mention that this can be also written as z e to the I theta. Okay, so I hope that this is clear. And what's the complex conjugate of a real number? So first of all, we denote it as z star or z dagger. Okay, and it is exactly what you think. So you know, it's just so if oh sorry. Yeah, so if z is a plus bi, then the complex conjugate is simply a minus bi. Okay, and you can observe very easily that the absolute value of a complex number and its conjugate are the same. Okay, so you can see that here it's because you know, you're going to square the each coefficient, right. So minus b to the squared will be obviously the same as b to the squared. So you're going to end up with the same absolute value. Now what about the product of two complex numbers? So the product of two complex numbers, that's sort of easy to compute, right. So a1 plus b1i, a2 plus b2i, right. What is this going to be? It's going to be a1, a2 minus b1, b2, right, because you have I times I, which will become I squared, which is minus 1, right, plus I times b1, a2 plus a1, b2, right. And now if the product that you are taking is between a complex number and its own conjugate, then what's going to happen? So in that case, as you can see from this picture here, as you can see from this computation over here, we are just going to get you know, a plus ib, a minus ib, right. So this is going to be a squared minus I squared b squared, right, plus I ba minus I ba. So this will go away and this is just going to be a squared plus b squared, and this is just going to be z the whole squared, right. All right, good. Okay, good. Now what is the conjugate transpose of a vector? So far we have talked about just complex numbers, but obviously we need to move quickly to higher dimensions. So now if I have a complex vector A, right, which I have written down here as this column vector, then what is the conjugate transpose represented as you know, a dagger here? Well, you know, it's exactly what you would expect. So you take the transpose and you take the conjugate, right? So that's the conjugate transpose, not surprisingly, right? So this is just going to be this. And two vectors are going to be called orthonormal if you know, if a dagger b is 0. So again, this is as we have seen before. Moreover, unsurprisingly, I can extend these ideas to matrices, right. So what's going to be the conjugate transpose of a matrix? Exactly what you expect. So you look at each column, you transpose it and you conjugate each entry. Yeah, so you first take the transpose and then replace each entry by its complex conjugate. Good. Okay, so now let's talk about something very cool, which is also something which unfortunately we won't dwell on too much in this class, which is the origins of quantum mechanics, right. So where is this idea coming from? This idea that a bit is both 0 and 1 at the same time, the quantum notion of a bit, this is a fairly revolutionary idea. It's not something that we are easily able to imagine even today, I think. So how did this all happen? Right, so the origins of this idea were in the so-called double slit experiment by Young, and this is the setup of the experiment. So what's happening here? As you can see, this is called the double slit experiment because you have two slits over here, right, in this partition, and you have a light source which is it is sending light to this partition. So the light passes through both these slits, and then collecting this light is a screen, right. So here is the screen that you have. So light is passing through these slits, and there is some observed pattern on the screen that lies ahead of it. Now typically we think, well, it depends who you are, I guess, but typically we think of light as either a wave or a particle. So we know that particles of light are called photons, but we also say things like rays of light, waves of light, and so on. So let's see what this experiment is showing us. So one of the first things that's observed here is that if I pass a photon beam, or light through these two slits, then it shows some wave like behavior, in the sense that as you can see in this picture here, right. So it sort of traverses as these waves, and then what is happening is that across the two slits, these waves are interfering, right. So this is what waves will do. So they interfere, which means that at some points there is constructive interference, and at some points there is destructive interference, and this matches up with what you see on the screen, which are a pattern of light and dark bands. So where there is constructive interference, you observe dark bands. Where there is destructive interference, you observe light bands, and this suggests that light is behaving like a wave. On the other hand, now what happens if I don't allow light to go through both the slits, but instead I either close off one slit, so maybe I close this off, or alternately maybe I measure over here, right. So I place my screen sort of right in front of one of the two slits. In this case, what happens is different. So when passed through one slit at a time, or observed using detectors in front of each slit, there is in fact no interference pattern. Okay, so in that case, what you observe is, as we see in this picture here, we see a particle pattern. So basically, we had these two slits here, right? Okay, and if I just measure over here, right, I close this and I measure over here, then I get sort of one bright band over here, and similarly if I measure over here, then I get another band here. So this is like this particle pattern. So basically, if I don't observe like I did in the previous case, then the outcome that I get is showing that light is behaving as a particle. So without observation, the photon was sorry, let me say that again. So if I don't observe, right, then the photon is in the position of both the states top and bottom at the same time. So that is what we saw in the previous slide. Whereas if I observe, right, if I observe just as it comes out of one slit, right, then I get the particle like behavior. So what is really happening is that here in the previous slide, when we don't observe when the light comes through the slit, if we don't observe then and there, then light is somehow going through both the slits at the same time. Okay, so this shows that light behaves as a wave and a particle depending on depending on the observation. Okay, and when it is not observed, then as I already said, then the photon is in the position of both states top and bottom at the same time, and this is the sort of superposition that quantum computing is going to make use of. Okay. So, just to summarize, when passed through one slit at a time or observed using detectors in front of each slit, light behaves as a particle, there is no interference pattern, but observation collapses the wave function of the particle, making it behave like a particle, right. So, without observation, the photon was in position of two states top and bottom, going through both at the same time, and this is the sort of superposition or parallelism that we are going to try to make use of in quantum computing. So, here is a nice picture that illustrates the idea, right. So, what is our normal idea of computing? In classical computing, what's going to happen is that you have let's say that you have some task. So, you have some lock over here and you want to check which key fits. Okay. Now, in serial computing, what you do is that you take the lock, right, and you try one key at a time. Now, you could imagine parallelizing this, but then you need that many locks. So, that is what happens in parallel computing. So, then you have many different locks and you can simultaneously try the keys in all of the locks. So, this is faster, right, than the serial computing setup, but this is resource inefficient, right, because you need that many locks. And what quantum computing is somehow doing is that you don't need this replication, because nature in some sense already provides it. Nature already provides this superposition. So, it is like saying that I am going to actually try all keys in parallel for the same lock. So, this is a little bit mind boggling for those of us who have grown up in classical computer science. And at the beginning, when we first encountered this idea, this seems like, oh, I mean, this is completely revolutionary. In fact, it is, but it is not as simple as we might think when we first look at it. So, it is not so simple as saying that I can in fact just try all the keys in the same lock at the same time and figure out which one works immediately in the same time that it would take me to try out one lock and key pair. It's not as simple as that. So, what is the catch? Okay, so why is this not completely sort of trivializing computing? If I can get this kind of an exponential speed up, then why does it not trivialize computing? So, let us go into that. Okay. So, now let us say that each register simultaneously stores both bits 0 and 1, then how many bits do n registers store? Well, 2 to the n, right. Now, this is an exponential number of bits. So, can we run exponentially many threads of computation in parallel? If we can, right, then can't we just solve all NP complete problems? This is the question. Okay. And it turns out that no, we can't, unsurprisingly, or you would have read it in the news many years ago. But why is that? So, it is because possibly I can simultaneously try an exponential number of solutions, but I cannot access these exponentially many answers easily. So, whatever is my problem, right. So, let us take our favorite NP complete problem, I do not know, the traveling salesperson problem or something, right, or the subset sum problem. So, in the subset sum problem, as you know, I have a bunch of objects, each object has some value and weight, and I have some knapsack. Right, this is, I guess, the general knapsack problem I am talking about. So, I have a knapsack, it has some capacity. I want to put as many objects in the knapsack that I can to maximize the value, right? This is the knapsack problem. So now a trivial algorithm for this problem is, well, just try all possible combinations, right? This is a trivial algorithm, and at the outset, just based on what I've told you so far, one might think that, well, let a quantum computer in parallel try all these different combinations. And what I'm saying now is that yes, maybe it can, but finally, right, I need to select the answer, I need to access the answer. And it turns out that, these computations are only accessible via what we call a measurement in quantum computing. Okay, so we can only access the answer by performing this so-called measurement. We'll talk a little more about it. And what this measurement does is it gives us whatever is, the highest probability outcome in some sense. So we'll get into this in more detail, but basically all that I want to convey here is this intuition that, yes, maybe you can in parallel try many different things, but you have to very quickly, your algorithm has to very quickly concentrate the probability on the correct solution, so that when you measure, you get the correct solution as the output. Okay, and this is something that in fact we don't know how to do for NP complete problems, at least. So in some cases, we are going to see in the course, in some cases we can get exponential speedups than what we knew before, but in many cases we cannot. Okay, so let's go back to our formalism. Okay, so first of all, given all the discussion around qubits, it's kind of high time we define them. So in order to define a qubit, I want to introduce the so-called bracket notation. Okay, so this bracket is broken into a ket and a bra, and this is how we define. So a ket is a d-dimensional column vector okay, in the complex space, so C to the D. Oh, and I should have said that it's represented like this. Okay, it's sort of opposite, which is, the bra part of the bracket is denoted as shown here, and this is a d-dimensional, as you can expect, row vector, right, which happens to be the complex conjugate of the corresponding ket vector. Okay, good. So, we write it like this. So, here's a ket, okay, or you have V2, which is some B1 up to BD, where the AI, BI are complex numbers. And the inner product is exactly what you would expect. So, the inner product of V1, V2, which is written like this, is, well, it's the inner product of the two vectors. But so I'm taking the complex conjugate of V1, right? So I'm taking the bra of V1 over here. So I'm going to get AI star BI. Okay, so this is some notation. And now, in order to proceed further with defining our qubit, what we are going to do is that, aided with this new notation that we have just developed, we are going to actually take our classical bits 0 and 1 and we will write them as vectors. Okay, so we are writing ket 0 here. So this we write as 1 0, and Ket-1 we write as 0, 1. Okay. And now we're finally ready to define our famous quantum bit over here. So, a qubit now is basically a linear combination of these classical bits. Okay, so this is formalizing the idea that it's somehow both at the same time, right? So, we define an arbitrary qubit ket psi, for instance, as alpha 0 plus alpha ket 0 plus beta ket 1. Now, here it is very important to note this normalization condition. Okay, so we can't just use any weights of our choice. Okay, they have to satisfy the condition that mod alpha squared plus mod beta squared should be 1, and these alpha and beta are the amplitudes on each of the basis states 0 and 1. Okay. So now what is the probability? Let us say that our psi is alpha 0 plus beta 1. If I measure psi, right, so if I measure this quantum state, what is the probability of finding it in either state 0 or state 1? So, for instance, again at a high level, thinking back of the double slit experiment, we were saying that when we perform the measurement, this collapses the wave function, right. So, now coming back to our qubit, as I said, it is somehow in a superposition of both 0 and 1. How do I access something out of it? So, what I am going to do is I am going to measure this qubit, and when I measure it, in fact, what is going to happen is that I am going to I am going to collapse it to one of the basis states, right. So, here 0 or 1, and the probability that I get either 0 or 1 is basically alpha squared or beta squared. So, this is for finding it in 0 and this is for finding it in 1. Okay. And now any two-state quantum system can be written as a linear combination of these basis states. Okay, so in particular, I can write any two-state quantum system as a matrix. Okay, so if I have, for example, I don't know, I have psi, let us say, as 0.80 plus 0.61, let us say, then I can write psi as 0.8, 0.6. I can write it in this form.